Hello and welcome to Project 152, your weekly exam prep. Every week we go through questions from the QCAA. If you stick with us every week, you'll have done every single question the QCAA has ever done. This week it is week 11. Let's get into it. So we're looking at subsets of the complex plane here, and it's a pretty tricky one. Let's take this equation here and just write it down. Okay, what does it mean? It says the angle of this complex number, or the argument of this complex number, all of it together, plus pi on 4 is equal to 0. Still doesn't make a lot of sense to me. What if I just rearrange it a little bit, move that to here? Feels like it makes a little more sense here. The argument, the angle of all of this complex number is equal to negative pi on 4. Okay, I'm just going to replace this with u. Sometimes when I see something complicated, just replacing it with u makes my life easier. All right, so we're looking at a subset where the argument of this is equal to negative pi on 4. That's super simple. The argument, all complex numbers with a argument of negative pi on 4 looks like that, not including 0. Okay. So that feels pretty good, and it brings my eye to these two as our options, right? But of course, the problem is that we're not dealing with u. We're actually looking at this thing here. So u wasn't u. U was equal to z plus I minus 1. Now, we can think about u as having a boundary here at 0. So if u has a boundary at 0, what does z have a boundary at? Well, let's let u equal 0 and find out. If u equals 0, z plus I minus 1. And that means that z equals 1 minus I. So our boundary is not at 0. Our boundary is actually at 1 minus I. Which one of these two has a boundary of 1 minus I? Right there. Our answer is B. Okay, what if you're not sure? What if you think maybe I'm wrong, but you're still tossing up between these two? Well, you could sub in 0. You could sub 0 into here, right? Or in here, doesn't matter. But if I sub 0 into here, I get argument of I minus 1 is equal to negative pi on 4. Well, that's not true. The argument of I minus 1 is, it's like that. It's like 3 pi on 4. So that doesn't work. So that one doesn't work. This one does work. All right, celebrating. Next question. So a very straightforward kind of question here because they tell you what to do. Using the substitution, this, determine this. Let's write it down. Now they tell me to replace tan x with u, so I'll just do that. And I've done it, but it's not at all helpful. In fact, it feels unhelpful because now I've got a u and an x. But that's not the point of substitution. The point of substitution is that there must be some kind of relationship between these two. If I had a formula sheet, then I would know what that relationship was. So if u is equal to tan x, then the derivative of u with respect to x is equal to sec squared x, according to my formula sheet. I can rearrange that so that I can have it as just dx, right? So dx is equal to du sec squared x. And then I can put that in right there. And now we see the magic of substitution, right? Because now we've got a sec squared x and a sec squared x, and it's simply u with respect to u. Integrating that is method stuff. Increase the power by 1, divide by the new power, so half u squared. Don't forget a plus c on the end. But u was never u. U is tan x. So half tan. We can say tan x squared, but when we're dealing with trig, tan squared x is the same thing. Can I see that up there? I believe I can. Half tan squared x plus c. The answer is B. Very straightforward. Last multiple choice question coming up. So a proof by induction question. It's been a little while since we've done one of these. What's it asking for? Which statement would be correct in the proof of the inductive step? All right, so the inductive step when you're doing proof by induction, it's the k plus 1 bit. It's, well, okay, if it was true for k, prove that it's true for k plus 1. So basically, we've got to take our equation here and replace n with k plus 1. All right, so I've just written it out, and now I'm going to replace n with k plus 1, and n with k plus 1, and n with k plus 1. Not forgetting those brackets there, because it all needs to be multiplied with that theta. All right, so can I see an option that looks exactly like what I have right there? I think I can. Option D. Super simple question, just jumping into the middle of proof by induction. That's the short responses, celebrate, and let's move on. So what do we have here? We have a three-dimensional picture, right? And a whole bunch of points, etc., etc., etc. Now, be careful, you need to look at your orientations. We've got X shooting out this way, we've got Y shooting out this way, and we've got Z shooting out of the page. You can make choices there, but anyway, that's what we've got, and we've got all this stuff here. Now, it says OABC is a parallelogram. That's important information. Okay, finally, determine the coordinates of B. All right, so we're trying to find the coordinates of B. Now, handily, we know the coordinates of A, and we know the coordinates of C, and we know O is the origin. Okay, that's A. And that is C right there, 3, 1, 2. So I'm going to draw this as a vector, right? So from here to there, that's a vector. From O to C is a vector. From O to A, that's also a vector. So I'll put a little arrowhead on there as well. Now, if I want to know the coordinates of B, right, what I need to note is that this is a parallelogram. So this line here is parallel, let's draw it here, to that line there, and this line is parallel to that line there. Not only are they parallel, they are also the same length. This and this are the same length. So if they're parallel, if they're going in the same direction and they're the same length, then they're literally the same vector. This vector is equal to this vector here. So why am I talking about this? Because I can say that vector OB, and thus the point B, is equal to vector OA plus vector OC, because this is OC. So OB is equal to OA plus OC. And I know what OA is, and I know what OC is. All right, so OA was this, OC was this. Adding them together, I get -3, 3, 0. The coordinates of B are -3, 3, 0. Now that is a 1-mark question, so you've really just got to write the answer down. I'm going to move this stuff out of the way because I've got some more stuff to do. Okay, so part B, we're starting here. M is the midpoint of BC. So there's M right there. And it's the midpoint of B and C. And they're asking me to determine the vector that represents OM. All right, so I'm coming up with that vector right there. Now we have a midpoint formula for vectors. We can say that the midpoint of those two vectors, so OM, is going to be equal to OB plus OC, but half of it. Half of OB plus OC. Now I know what OB is because I just calculated it. I know what OC is because they told me it. So that's it. There we go. So we've got half of OB, which I knew, plus OC. OB plus OC is this, and half of it is that, and my answer is 0, 2, 1. Now you'll notice this is a 1 marker as well, so even if you've done all this working, or you've just kind of worked it out in your head somehow, 0, 2, 1, we only need the answer. Okay, so part C. Part C starts here with the statement, N divides AM in the ratio 2 to 1. Okay, N divides A and M in the ratio 2 to 1. All right, let me just write that in. It's a very non-standard thing for me to do here. I'm just saying that this is 2 units, but who knows how long those units are. They're not the same units as this. This is double the length of this. All right, so those 2's and 1's, that's non-standard mathematical stuff. I'm just writing it down to give myself a sense that this is twice as big as just this length here. All right, what am I trying to determine? I'm trying to determine the vector ON. So from here to here. All right, I love this kind of question. It is a question that students have some trouble with. So getting from O to N, from there to there, you've just got to find a path to travel along, right? And by that I mean, like, look at all the vectors you know. We know OA, we know AB, we know BN. We've got all these lines, right? We've just got to travel along some lines to get to where we want to get to. Now, I think there's like 10 million different ways that you could solve this, but I'm going to solve it by traveling from O to A, and then from A to N. So I'm going to travel along here, and I'm going to travel along here. Because I can say that vector ON is equal to vector OA plus vector AN. We're doing like a linear combination of vectors to come up with this vector here. Okay, luckily I already know what vector OA is. It's this, -6, 2, -2. Now, what do I know about AN? Well, AN is a fraction of AM, right? And I feel like because I know what point M is, finding vector AM is like a stepping stone to finding vector AN. All right, so, and you got to be careful here, and this is sort of my non-standard notation. Vector AM is broken into 3 parts. 2 of those parts are A and N. So AN is equal to 2/3 of vector AM. Don't really need those brackets there. All right, so I'm cooking with gas. I don't know what vector AM is yet, but I think I know how to find it, right? Because this remains to -2, right? We've got our 2/3 here. AM can be found. If I want to know what this vector is here, I've got a simple formula for that. OM plus OA. Sorry, minus OA. This should be the kind of thing you do all of the time. If you're trying to find vector AB, usually it's AB. If you're trying to find vector AB, it's OB minus OA. It's the second one minus the first one. All right, and amazingly, I know both of those things, right? Because I've got -6, 2, -2 there. I've got 2/3. Now, OM, I found that here. 0, 2, 1. And now I'm subtracting OA, and I know what OA is. It's -6, 2, -2. All right, so subtract those from each other and then multiply it by 2/3. So adding those together, I get 603. Multiplying it by 2/3, I get 402. And then run out of space, I'll just do it over here. -6 plus 4 is -2. 2 plus 0 is 2. And -2 plus 2 is 0. My final answer is that vector ON is equal to -2 to 0. Now, I've just written my answer again. I've realized that my answers, I'm not happy with these two. Because this one says determine the coordinates. That's right. But this one says determine the vectors. We don't write vectors like that. Let me fix that. All right, and our last bit of the question, use a vector method to show that O, B, and N lie on a straight line. All right, so O, B, and then we've got N here. Or O, B, and N. Okay, these all need to lie on a straight line. Okay, there is something really nice that we can do here. First of all, we need to note that, okay, O, B, and O, N both have a common starting point. OB, ON, common start point. All right, so it's possible, right? Okay, now, if they're in a straight line, that means that they must be moving in the same direction. So if they're moving in the same direction, the vector ON and the vector OB must be multiples of each other. So we can say something like OB is equal to KON. Now that's a vector, that's a vector, that's a vector, that's a vector. All right, so what are we saying? We're saying that, well, if we take ON and multiply it by some factor, we'll have scaled it up to vector OB. And if we've done that, if we can show that these things are true, we're in business. Okay, so we know what vector OB is. Okay, so this is like, I guess we're required to prove that this is true, right? So let's set up a left-hand side for our OB. It's negative 3, 3, 0. All right, let's set up a right-hand side, K, ON. And we've already showed that ON is negative 2, 2, 0. Okay, now, is there some K value that I can put in here that would scale this up to be this? Yes, there is. If I scale this up by 3 over 2, negative 2, 2, 0, let's see what we get. We get negative 6 divided by 2, which is 3. We get 6 over 2, which is 3. And we get 3 over 2 times 0, which is 0. Done. The left-hand side equals the right-hand side. We have shown it. Use a vector method to show. I think that's what I just did. All right, that's important to note. Parallel vectors, you create this nice little thing. You go from there. Celebrate, and I've got one more to go today. All right, so last question here. We've got velocity vectors for 2 objects. So 2 velocity vectors here. And what's going to happen? We're going to try to find the time when they're exactly 4 meters away from each other. Okay, so we want to know about their positions. So we need 2 position vectors. If we've got velocity vectors, their position vectors are going to be the integrals of those. So this is our first one, and we need to find the integral of that. Now that's pretty straightforward methods-y kind of stuff. So there's our integral, and of course we need a plus c on the end. Okay, so in order to find that plus c, we need some more information about its position, and we have here an initial position of negative 2, 0, 2. Okay, so that means at time 0, that is our position. So let's put that in. So there's our initial position and time 0. So 3 times time 0 is 0. 3 times time 0 is 0. Now you've got to be a little bit careful here because cos of 0 is 1. So negative 2 times 1 is negative 2. But sine 0 is 0, so all of that is 0 there. And then we have our plus c. Now of course that means that our negative 2's will cancel each other out. And that means that our c value is simply 2k. So finishing that off now, we know that our displacement vector is equal, or displacement function is equal to all of this plus 2k. So great, we have a displacement vector function for our first one. That was my dog. So I've just taken that, I'm putting it there, and now I'm going to get rid of all this just to make myself some space, and I'm going to do the same thing for our second particle. Alright, so this is our second particle. We're integrating our velocity function. I forgot the with respect to t last time, so put that back in there. Let's go. That one's easy. Now, of course, we've got this pesky plus c here, but luckily we have an initial position, so we can put that initial position in and do the same thing again, solve for c. Okay, so we've got our time of 0 here. We're doing the same thing again. Sine 0i, that's a big 0 there. This is 1. This is 1, so that's just j, and then we've got our c here. So there's a 0, so we can get rid of that. We've just got j plus c equals j minus k, which means that the j's can cancel each other out. We've got a c equal to negative k, which means now that I know that c is equal to negative k, this is our displacement function. Sin ti plus cos tj minus k. All right, that's great. We've got 2 displacement functions there, one for object A, one for object B. Let's get rid of this, move on to our next little piece. All right, so what's the question interested in? Determine the position of object A when it is 4 meters away from object B. So drawing a picture, we've got object A here, and that's like moving somewhere. We've got object B here. We're very interested in the distance between these 2 objects. So actually, let's draw it a little more like this. We're very interested in the distance between these 2 objects. So what I'm really interested in is a vector function that describes this arrow. So I'm interested in the vector function RB minus RA, because this vector function describes this vector function describes this. So if I subtract one vector function from the other, I get my nice vector here. All right, it's a lot to take in, but let's take a look at what's going on here. We're doing RB minus RA, so we subtract the I components. So sine t minus minus. That's how I end up with this plus 2 cos 3t. Now all of that's I components. And then we have positive cos t minus 2 sine 3t, so there, and that's j components. And then I have a minus 1k, minus 1 minus positive 2, so minus 1 minus 2. So that we can simplify a little bit to just be minus 3k. So a reminder, what I've found here, what this big thing is the vector function that describes this arrow. Now A is moving and B is moving, and so this arrow might get larger and smaller. What I'm interested in is not the direction of the arrow, that's not interesting to me at all. What I'm interested in is the magnitude of this vector. Now, the magnitude will be this squared plus this squared plus this squared square root. We're getting monstrous here. Okay, that's what it looks like. Now, I need to expand this bracket. So it's going to be like this squared, and then multiply this by this, and then this squared, and then expand this bracket, and then expand this bracket as well. Lots of work to do. So this is just my first bracket. This squared, 2 lots of this times this, and then this squared right here. You're not squaring the 3t, that's inside of our little bracket here. You're squaring the rest of it. Okay, I still haven't done this. That's it. That's the whole monstrous thing. We've got our plus 9 here on the end here. And these 3 terms, this term, and this term, it's just the expansion of this set of brackets. Okay, there must be a way to start simplifying this. All right, so we'll do it in stages. We see sine squared t and cos squared t. And I've written them here because that's the Pythagorean identity. So that piece here is just going to be a 1. And we can do it one more time because I see 4 cos squared 3t and 4 sine squared 3t. So if I take those two and factorize them, so factorize the 4 out here, I get cos squared 3t plus sine squared 3t. That's another Pythagorean identity, so that's equal to 1, and then I've got 4 times 1. So that whole thing is just equal to 4. Okay, so I must have done quite a bit now. I've done this sine squared, I've done this bit here, I've done this bit here, and I've done this bit here. Okay, so while I'm dealing with numbers over here, I also have this plus 9. Okay, good, so I've dealt with that one there. And then what do I have left? I have this thing here, and I have this thing here. Now, it's at this point that being very familiar with the trig identities, or at least knowing how to use your formula sheet, is a good idea, because we have this, which means that we can simplify this wild thing here, sine, cos, sine, into a simple sine A minus B. So if we're subbing this in, so we've got sine t cos 3t minus cos t sine 3t, a very neat little pattern. So putting that into our formula, we get 14 plus 4, and then it's just going to be sine. Now, what's our A value? T, and then what's our B value? 3t. So t minus 3t, so that's negative 2t. 14 plus 4 sine negative 2t. We've gone through all of this stuff. We've got this. What is this again? Oh, yeah. I need square roots over everything. Square roots, square roots, square roots, square roots. Because this is supposed to be the distance, the magnitude of our arrow. Now that we know that our arrow is this long, we want to know when does this value equal 4? Because we want to know when is our arrow 4 meters long, when is our vector 4 meters long, when our object's 4 units apart. So 4 equals that. Now running out of space, but we'll get there. If I square both sides, it's going to be 16 equals 14 plus 4 sine negative 2t. 16 minus 14. So I'm going to have 2 equals 4 sine negative 2t. All right, I'm definitely out of space now. All right, I'll fix that up. Now we can keep going. Squaring both sides, we get 16 equals 14 plus 4 sine negative 2t, something like that. Subtracting 14 from both sides, 2 equals 4 sine negative 2t. dividing by 4 on both sides, we'll get 2 divided by 4, which is 1/2 sine negative 2t. Ugh. Alright, now we're basically solving this trig here. Now a neat little trick you can do when solving this trig equation, because it's a sine equation, this statement, sine negative 2t, is equal to 1/2 equals negative sine positive 2t. Now, don't try that with cos, it's not going to work, but it's because of the fact that sine is positive here and negative here, and it like flips over. So a negative angle here is the same, and a positive here is the same as having a positive angle here, and negative amplitude. You can graph those two and you'll see they look exactly the same. Okay, so that means that I'm solving, let's write it here, sine 2t equals negative 1/2 now. Okay, now we can unit circle that. If we just ignore that it says 2t for the moment, we're just solving for like theta. In there, it's going to be 7 pi on 6. Now you might be thinking to yourself, yeah, but aren't there like lots and lots and lots of solutions? It says here the first time. So we're just interested in this very first answer. So therefore 2t equals 7 pi on 6, which means that t equals 7 pi on 12. Now are we finished? Not quite. What we have is the time at which the distance between these two objects is 4 meters. But that, of course, is not what the question says. It says determine the position of object A when that's happening. So in order for us to do that, we need to take our position and sub in this value, 7 pi on 12 for time. That's relatively easy. Okay, there it is with 7 pi on 12 subbed in for all of the times. This is going to simplify as 7 pi on 4. So is this 7 pi on 4, and that 2k stays as it is. All right, we are finished. Our final answer is going to be, so 7 pi on 4 is that angle right there. The value, or the absolute value of it, is root 2 on 2. So we've got negative 2 times root 2 on 2. Cos in this quadrant, so that's positive, and that's the I component, and then 2 sine 7 pi on 4, so that's 2 times root 2 on 2, but it's sine in that quadrant, so it's negative, and then, okay, all right, that's our J component. All right, and you can see this negative 2 and this 2, they're going to cancel each other out. We're left with negative root 2i plus, we've also got another negative root 2j, and we've got this final one, k. That is it. That is the position of our object. I think that is worth a celebrate. Bam! And that is it for Project 152 for another week. Now go and check out next week's questions. I've already written them. They are a little shorter than previous weeks. The thinking is that you've sort of finished most of the Unit 3 questions. You're still learning a little bit of Unit 4. So for the next few weeks, we're going to be doing slightly less questions, 3 or 4 questions a week. And then as we get closer to finishing Unit 4 and then having finished Unit 4, we're going to add up some more questions onto it. Stick with me though, because I will do the maths for you. By the time we get to the external exam, we'll have done every single question. Catch you next week.